Um, hello? Yes, mic is working. Hi. I brought a microphone with me today. It feels odd and cool, I guess. Let's see how it works. Because if I'm using this mic, it will look like I'm not using the keyboard or the mouse. We'll see. Good morning or any other time of day it is on your side. Hi. Good, maybe afternoon. I'm not sure. Yes. I was like, should I give in to laziness or should I stream? And then I was like, okay, maybe 1 hour is okay. Yeah. No, I'm trying to look like the YouTubers that hold a mic, but failing at it. It does look like stand-up, doesn't it? Yeah. Oh, hi. It's close to midnight. Whoa. Rexus? That's a really cool name. Well, good midnight. It's funny how some times of like cannot be used for good. Like you can't say good noon or good midnight because these are, yeah, I'm just remembering when we were studying English and how it's like at midnight or in the morning. This is how you use them. Ugh. Anyway, meta YouTubers holding, oh yeah, see that one. The meta of YouTubers holding mics is, really? Omnidirectional mic is not, okay. See, I don't have a clip-on, visual of a clip-on mic, and also, I know that meta, I'm sure you have watched the same video that I've watched about it by why did I forget the British YouTuber's name? Anyway, why not? Let's make good noon a thing. Yeah, I agree with you. Yeah, they mostly put it on like, it's either a spatula or a spoon or a fork, that sort of mic. Yeah. Anyway, I'm really behind on it, but hey. Supposedly we're here to study. Ta-da! I'm gonna high noon. Oh, high noon. Get it? Got it. Supposedly I'm going to study, but if I don't, that's cool. Because sometimes I talk too much and then I forget that I should be learning. So where were we? Let's do a quick recap. Processing the training data. Okay. So from the question answering part. Oh, we were supposed to split the context because they were too long, but the questions were fine. Okay, that's what I'm remembering. And internet is really good right now. I'm not going to jinx it. And I'm going to pray that it's going to be good this month. Yeah, we can see start of sentence and end of sentence. And these are indexes, maybe. Okay. Oh, this means, nope, I don't know what it means. Why is there one here, but not anywhere else? And then there's another one here. The answer is here. Ha 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 ha. Wow, got it. The answer is here. Okay. And all of them are other info. Cool. So that's what the index is. Meaning, is that where the answer is supposed to be? No? Ya Allah, oh my God. Okay, that scared me. In this case, context is not too long, right? But, it's fine. I'll repeat this part. Some of the examples in the data set have very long context that will exceed the maximum length. So this is the context. Cool. which is 384. Why? As we saw in chapter 6, when we explored the internals of the question answering pipeline, we will deal with long context by creating several training features from one sample of our dataset. Okay, with a sliding window between them. Got it. To see how this works using the current example, we can limit the length to 100. So we have a sliding window of 50 tokens, which is a lot, isn't it? Because like if your limit is 100, half of it is a sliding window, which is a lot. Don't get distracted. Do not get distracted. I am not distracted. Am I distracted? Just a little. Okay. There we go. Okay. So as a reminder, you have max length to set maximum length, which is 100. Truncation only second, meaning we have two parts. You only truncate the second part, which is the context, not the questions. Okay, sorry. Stride, to set the number of overlapping tokens between two successive chunks, being 50 here, just 50, okay. Return overflowing tokens to true because we don't want to lose any information. Nice. And that's that. Max length. We have question, context. This is the second part, which will be truncated. Max length, truncation, stride. I like the word stride. And then the overflowing tokens. Okay. And we are tokenizing the list of IDs, inputs. Where did we get them? Anyway, this is what we see. We see the question and then the truncated. This is only one, actually, right? Okay. And this is just one separated. All right. And then it says, right. Okay. As we can see, I should do this, right? Yeah. Okay. Our example has been split into 4 inputs, each of them containing the question and some part of the context. Note that the answer here is apparently in the last part, right? Third and last. Ah, nice. So it is split into 2 parts. This is last, and then third here. So by dealing with long context in this way, we will create some training examples where the answer is not included in the context. Huh? Hold up, what did you say? Dealing with long context this way, we will create, there will be some examples. So here, 2 out of 4 don't have the answer. Okay. For those examples, the label will be everything will be 0. We will set those labels in the unfortunate case where the answer has been truncated, so that the start and we only have start and end. For the examples where the answer is in the context, label will be index of the token where it starts and where it ends, as we saw up there. Okay. The dataset provides us with the start character of the answer in the context, right? So here. Oh, okay. Where is it? And by adding the length of the answer, we can find the end character. So we get start and it, and then you check the length as, I remember that. To map those tokens to indices, we will need to use the offset mappings. We can have our tokenizer return these by passing along return offset mapping to true. Okay. As we can see, we get, oh, I'm supposed to run this. I mean, I already did. There it is. Okay. We get back the usual input IDs, which is here, and then token type IDs, attention mask, as well as offset mapping that we asked for, and then the overflow to sample mapping. The corresponding value will be of use to us when we tokenize the several texts at the same time. Okay, which we should do to benefit from the fact that our tokenizer is backed by Rust. Oh, parallel. Okay. Since one sample can give several features, it maps each to the example it originated from, because here we only tokenized one. We get list of zeros. Okay, got it. Thank you. But if we tokenize more, that's what it means. This 1, 2, 3, 4, 5, because we're tokenizing 20 to 26. So this is just the corresponding index. Thank you. Okay, now I get it. Let's move on. As we can see, the first three examples at indices 2, 3, and 4 in the training set. Oh, okay. Each give 4 features. So this has 1, 2, 3, 4, and this has, no, it doesn't. Oh, this does. All of them have 4. And the last example at index 5 gave 5. Cool. Good to know. No, gave 7. All right. This information will be useful to map each feature we get to its corresponding label. As mentioned earlier, those labels are 0, 0 if the answer is not in the corresponding span of the context. Yes, but if it is, we get the start and end. Or start and end. Oh my God. I think I got bit by a mosquito. I don't like this. There is literally one mosquito in this place, and I failed to kill it. If the answer is in the corresponding span of the context, with start position being the index of the token and the input IDs, and the start of the answer, right? Yes. Index at the start of the answer and being index at the end. Yes. Why are you repeating something that you said multiple times? To determine which of these, I guess it's repeating itself multiple times for people like me who don't pay attention. Okay. Is the case, and if relevant, the position of the tokens, we first find the indices that start and end the context in the input IDs. Oh my God, I can't focus. I got nothing. Let's do this. Okay. To determine which of these is the case, and if relevant, the position of the tokens, we first find indices that start and end. Okay, I think I got it. So we just want to find the answer. Oh my God, 3 mosquitoes falling into coffee. Oof, that's tough. I'm trying to kill it. I have 2 methods. One of them is, you clap your hand and you can trap it. The second one is you grab it. I like that because it feels like I'm being Jackie Chan. Yeah, I mean, it's really cold, so mosquitoes should be dead, but some of them have come inside and just made, I don't know, I'm sure they're growing, the numbers, those that are inside. So yeah, I've been trying to kill them on a daily basis. I feel like a murderer, but a justified one. Yeah. Because like they're not supposed to be around during the winter. But here we are. I don't know about mosquitoes falling into food, but I know about flies. I mean, yeah. Anyway, the whole thing about their wings. We could use token type IDs to do this, but since those do not necessarily exist for all models, Dilbert does not require them. All right. We will use sequence ID. Oh, I don't think we've used that. Method for batch encoding or tokenizer return. So the output, something, oh, in the sea, you're in the sea? Electric swatter. We used to have it actually. We used to have one. We're using a different thing. The thing that it's like a diffuser. Okay. Nope. I did not got it. All right. My hand is a swatter. I recall mosquitoes larvae coming out of the water from the taps. You're kidding. Oh my god. Ooh. So like they died in the tank, right? Whoa, that's crazy. They are number one killers, aren't they? Like they are the most, the thing that kills humans the most. Not even humans can pass them yet. We'll try though. I'm sure we'll try. Sequence ID. Oh, we have used this, haven't we? Oh God, they live in the water, living ones? That is so, that is information I did not need in this morning. That has not happened to me yet. Yeah, we live in a place that has a lot of mosquitoes. Like I am sort of used to it. That's why I'm really good at killing them. It's not the same for, it depends on even the neighborhood, doesn't it? If you live by greenery, you'll get mosquitoes, right? So I should move to the desert. No, I like living around greenery. It's one thing that I can sacrifice, being away from people, close to greenery, and close to, I guess, flies and mosquitoes. That one is not by choice. Once we have these token indices, we look at corresponding offsets, which are tuples. I forgot how to say this one. I feel like saying tuple, but no, I think it's tuple. Anyway, two integers representing the span of characters inside the original context. Okay, we can thus detect if the chunk of the context in this feature starts after the answer or ends before the answer begins. Chunk of the context. Okay. How would we know if it's from a different oh god, anyway, how would we, if I want to kill the mosquito so bad, how would we know the context thing if it's not in it? We get 0, 0. Got it. I forgot. Okay. So if we get 0, 0, it means the answer is not in this chunk, right? Okay. So we're testing it on those 4 answers, and we're looping through them, right? Input, offset. Oh, okay. So here, this is our inputs. Because I used it on 20 to 26, I'm going to do that here as well. But it's using it on 2 to 6. So our answer will be different, which is nice. There we go. Oh no, this looks ugly. Do I have to do a T for it to look normal? So we have a bunch of 0 and then number 0, number 0, number 0. Are these numbers start and end of answers? Supposedly, right? Let's look at this one here as well. Number 0, number 0. Let's look at a few results to verify that our approach is correct. For the first feature, we find 83. Where's 85? Oh, here. As labels. So let's compare the theoretical answer with the decoded span of tokens from 83 to 85 inclusive. So this is like start and end. Odd. That is odd. So I have a 0, but then I have an 81. And then an 83 here. All right. So what does this do? It gets overflow to sample mapping, and then this is our ID. We look at the answer to get the ID, start and end, start to end, and then we decode it. So the answer is, oh, I didn't get the question though. Learning center. Label gives nothing because it was 0. See, I'm not wrong about this, right? We got 0. So that's a mistake. Did you get the right one? They got the right one. Boo. Okay, it's a match for you, not for me. That's fine. Okay, another index. Oh, so that was index 0. I can check another index. Let's just, yeah, that's wrong. Index 0. Why? Where is index 0 coming from? Let's go for 2. Oh, see, now that's correct. Ah, which is 50? Huh. For 4, we don't, okay. Hold up. For you, 1, 2, 3, 4 is not the answer. And 0 is not the answer for me. Got it. I did. Okay. No. Okay. I'm not going to do those homeworks. Now that we have seen step by step how to pre-process our training data, we can group it in a function we will apply on the whole training. Yes, because these were all just tests. Tests. Yeah, we were just testing how to process data. We'll pad every feature to the maximum length we set, as most of the context will be long, except for the last one, right? And the corresponding sample will be split into several features. So there is no real benefit to applying dynamic padding here. Okay. All right. So this is our max length. Our stride is different. This is the thing that we did a while back. This is just everything put together. Find start and end of context from index 0. Answer is not inside label 0, 0. Otherwise, something about the start and end. Okay, cool. And And then this is start and end. So we make them. They don't exist. Cool. Is it here? Theoretical answer 5. No, not here. Okay. For this one, okay, so it was all right. This is the thing that should take time, right? No? Hold up. Map, yes. Okay, training. What is it called? Pre-processed training examples. Pre-processed training examples. So if I run this, yeah, should take a while. Maybe not too long. Note that we define 2 constants to determine the maximum length. We did. As well as length of the sliding window, and that we added a tiny bit of cleanup before tokenizing. Some of the questions in the squad data set have extra spaces at the beginning and the end that don't add anything. Like what? Take up space being tokenized. So we removed, just extra spaces. Where? I didn't see it happen. Was it here? To apply this function on the whole training set, we use map and batched true. Was it batched? Oh, wow, that's nice. That's fast. Was it batched true that would get me errors sometimes? No, it was another thing. It was like how many was like a parallel thing. It's necessary here as we are changing the length of the data set. Right, since one example can give several training features. Cool. Okay. As you can see, the pre-processing added roughly, before and after. Oh, okay. 1,000 features, which is not that long. Not like, I am surprised. So not all of the contexts were that long. All right. So that was the training data. I'm out. That was the training data, and then the validation also needs processing. It is the same thing, huh? Then we get to the fine-tuning. I guess I can go through this one because it's basically the same thing. So before we forget, let's look at it, and then we'll move to something else. Yeah, same, got it. So for the validation thing, pre-processing the validation data will be slightly easier, thank you, as you don't need to guarantee labels unless we want to compute a validation loss, but that number won't be helpful, okay? It won't help us understand how good the model is. The real joy I'm like, wait, is my microphone omnidirectional? I don't think it is, my actual one. I'm gonna test it later. Okay, the real joy will be to interpret the predictions of them. Is that a joy? Predictions of the model into spans of original context. For this, we will just need to store both the offset mappings and some way to match each created feature to the original example. So do we just do the opposite of what we did to split it? Since there is an ID column in the original dataset, we'll use that ID. The only thing we'll add here is a tiny bit of cleanup of the offset mappings. They will contain offsets for the question and the context, but once we're in the post-processing stage, we won't have any way to know which part of input ID corresponds to the context and which part to the question. Really? So sequence ID method we use is available for the output of the tokenizer only, not, okay, not what? not the function we make. So we'll set the offset corresponding to the question. So for validation, we don't care about the question. We only want the answer. So that offset will be none. Cool. So here is the validation one. This is, I guess, our list of questions. Same thing. Pop. Input pop overflow to sample mapping, sample map. For all inputs, sample map I, meaning the one corresponding. Append sample IDs, and then input is the tokenizer output. Give me the sequence ID of this current one, and give me the offset mapping. And for that, if it's 1, make it none, else keep it. So now the questions become none. And then we apply it, and then that's it. In this case, we've only added a couple of 100 samples. It appears the context and the validation is shorter. And now that's done, we can do the training, which I'm not going to do because I am not feeling it. I am lazy right now. But what I will do that I feel like I have neglected is our lectures. What? I'm going to refresh this. Okay. So, oh, they're quiet for now. I remember this being a half lecture by Graham Neubig and then half by this guy, Nishant. And yeah, we just start here. Let me know about the sound quality, okay? Nothing yet. Oh, okay.
All right, can everyone hear me? Sweet. Okay, move this. It looks like I'm talking to someone instead of in between both of you. There's my mouse. All right, so hi everyone. I'm going to talk about model interpretability. For those who don't know me, I'm one of your TAs. I'm a first-year PhD student working with Mona Diab on model interpretability. Mouse. Where what do I click? Your mouse should be there. No, just... All right. So hi everyone. I'm going to talk about model interpretability. For those who don't know me, I'm one of your TAs. I'm a first-year PhD student.
Oh my
working with Mona Diab
God.
on model interpretability.
What happened? Okay, there we go. Sound is good.
What I want you to take away, if you fall asleep, this is too boring. Here are sort of the two main takeaways. One, I want to convince you that model interpretability is important to study.
I think sound is good, right? You can hear it as well as you hear me, right? Okay. Model interpretability. Okay.
Two, I want you to find this interesting, and something you want to explore more. There's a bunch of details here. This is going to be kind of a whirlwind tour. I'm not going to get super deep into anything. So hopefully this acts as a starting point, than anything else. So interpretability in AI.
Oh. Yeah. The sound got, I messed something up. I was just checking to see. Okay, that's good. You can hear. I was checking because, you know, I monitor the YouTube studio and Twitch stream manager. So I messed the audio there. Yeah, sorry about that.
The definition is it's the study of understanding the decisions that AI systems make and putting them into easily human understandable terms. This can mean a lot of different things, and this is often really hard. And the why is to use that understanding to iteratively better design systems that are better, they're more performant, but also those that are more human understandable. So interpretability is this big blob, but there's a bunch of other spheres that intersect with it. This is a super incomplete list. So bear with me, but causality and data integrate with this. There's aspects that are interpretable. There's aspects that matter here. Explainable AI is another thing that you've probably heard. This sits firmly in the interpretability blob and connects with ideas and causality.
I feel like we've heard about this quite a bit, like AI being a black box and we cannot understand what's going on inside. There, especially when it comes to like neural networks, right?
And data too. Model interpretability sits on this kind of other side of things. It intersects a little bit with causality and explainable AI, but is a little bit separate for it and from it.
Oh, wow. Is that what I was talking about?
And mechanistic interpretability, which you've probably heard of, it's gotten a lot of buzz recently, kind of sits inside of model interpretability. It's a special case of model interpretability. I hope the mech-interp people agree with me, but so historically we've been dealing with really, really, really small models. We had Bayes nets. This is a very small model. If all these are binary variables, this is 8 total parameters, and only 4 of which are independent. We also used to work with linear regression a lot. And in the first case, that's a nice line, can be 2 parameters. The multivariate case, again, that's a small number of parameters. We've moved to more things. We've moved to MLPs that have larger weight matrices, but all of these are kind of digestible.
Hey, MLPs. Multi-layer perceptrons, right?
And interpretable. So the interpretability world was sort of not super concerned with large, ginormous things, but we're not there anymore. This is a language model. This is still part of a language model. Now it's getting more and more.
Oh, I love the emoji.
And more hairy. And
dead.
This is just not interpretable. I mentioned on the first day of class that I hate when we update parameters of models. I also hate when models are this big. And this is a 6-layer transformer. This is way smaller than basic.
Nishant, hate is a strong word. Be nicer to models. They're trying their best.
Anything that we have. And this makes things very, very uninterpretable. So we'll talk about one way that people sort of 5 years ago started addressing this problem, and this is the idea of probing. So how do we make sense of a giant model? This is one way. So we take our giant model, we cut the top off basically, and now we have this thing. We stick a probe, which actually in a lot of cases looks very similar to a language modeling head. Usually it's a small 2-layer or 1-layer MLP. And we basically treat the model as something that exists, and we only really care about the output.
Yeah, but it's not the model's fault for being complex, you know. He said he hates that parameters need to be updated, right? That's what he said.
Of the model. So more specifically, what is a probe? It's a classifier, this green thing here, that is specifically trained to predict some specific property from the pre-trained model's representations alone. So in 2019, Ian Tenney and folks introduced edge probing. So this is a general method. It works to probe different types of information out of a model. So this bottom part here, this bottom part here You pass in a sequence, you pass it into a model. This is BERT in their experiments often, and that outputs a set of contextual vectors. These contextual vectors can be at any layer. Often it's near the top, but we'll talk about the fact that this can work kind of across layers, and different layers encode different information. And on top of this, you have this MLP that you train to output a prediction. Your model is always fixed in these cases. So you can do things like part of speech tagging, where each specific word you try to determine what its part of speech is. And in that case, these S1 and S2 spans here, only one of them is active because you're predicting for every single contextualized vector, you're predicting whether that thing is a noun or a verb or something like this. You can have other sorts of tasks too, like entailment, where you have two sequences and two spans, and you use the embeddings for those spans. For like sentence 1 and sentence 2, you pull them together in some way, and then you pass them to this MLP, and you see whether that MLP can solve that task. So they did this in another paper. BERT rediscovers the NLP pipeline, and there's a lot going on in this figure. The only major thing here to take away is these numbers that are in this like pink purple color. So these are a bunch of different properties, so part of speech, and a bunch of other things. And what they basically find is that at earlier layers in the model, the things that are closer to the token level representation are more extractable using a probe. And the things that require more contextualized information is extractable later, from later layers in the model. And so here's sort of a brief description of what these tasks are. So the ones on the bottom are more semantic, more contextualized, like semantic proto-roles and relation classification. And then the first few are more, chunking and part of speech tagging and dependency labeling in these sorts of tasks. So there's a bunch of issues with probing, and there aren't as many probing papers now as there were many years ago. And so if your probe, let's say your probe works, it's possible that the representation actually encodes that information. It's also possible that it doesn't, and the probe solved the task by itself. Keep in mind that you're learning this probe, you're training this probe on labeled data. Let's say your probe doesn't work. Does that tell you anything?
Probe solved the task by itself? How can we trust the probe?
Maybe not. Maybe the representation lacks the information, or maybe your probe isn't actually able to disentangle that information from your representation. Maybe the probe doesn't have the right function class. Maybe you poorly trained your probe. There's hyperparameters for your probe. So oftentimes your probe doesn't give you that much information. There's more problems too. So often we want to probe tasks themselves, and that requires a lot of supervised data. But we can't collect a lot of supervised data, so we collect some of it. And then that instead produces this convenient sample that we have that's a data set that is a convenient sample of your task. So really what you're probing is the data set. And so with all these limitations, it's fallen out of favor a little bit. It's still very, very useful, but it's fallen out of favor as like a core model interpretability idea. Also, probes designed in this way are correlated. They're correlative, not really causative. So your underlying model is trained in a specific way. All of that information is disentangled and kind of thrown away, and you're only looking at the output representation, and you're saying, is my output representation correlated to the thing that I'm training this probe for? There's no notion of intervening on this latent space. There's no notion of causation, really. So you're just seeing whether your representation is correlated with your property that you're probing for. And with these limitations, the community's moved a little bit away from this area.
Oh, so it's no longer like oh wow, I recognize one name here. Ooh, so even this research is about how it's not viable.
A bunch of other probing work. So a bunch of people aim to solve a bunch of these problems. And for the sake of time, I'm not going to go into all of these, but I'd encourage you to look into these. For some of these problems, they're able to control for like the complexity of the probe and things like this. But even despite that, probing is sort of slowly kind of falling out of favor. So before I move into model interpretability, are there any questions on probing?
Neuronpedia. Kind of cool demonstration. Right. Oh. So, what is that? I'm gonna look it up. Platform. Oh, hey. It's a this might be before the Golden Gate Bridge work. Yeah, that one was. It did well. Like it was a splash, you know. This is the thing you talked about. Here you go. It's by DeepMind. Oh, one day I'll work there, inshallah. Wait for me. I don't know why it feels fancy, DeepMind, you know? Oh, what is that? Oh, I don't know them. Okay. Cool. Open platform for interpretability research. And then we have visuals. Oh, hey. I do like cats. Let's take you. Why? This is not text? I can't copy this? And if I just... What is happening? Are these not text? Yeah. Okay, fine. I'll write something. Oh, there are examples. Just, yeah, give me a random one. Our. Comprehensive. Our. Oh. Sorry. Don't want to go too deep into it. This is Gemma. Nope. Gemma scope. Huh? What is that? Oh. It says Cobras, right? Why did this come here? What is happening? How is this related? Positive, negative. Right. Logits that are related. Our. Wait, who's our? Social media platform. For social. Okay, see, now that makes sense. Positive, negative. Influencer. Yeah, this looks really similar. A phrase into Gemma scope and see layer by layer. Not related, but the head activates strongly for all of those tokens. This is really cool. This, yeah, positive, negative logits. I see that. But I'm guessing this is a part of a longer top activation. This has to be a part of a longer thing, because in our, it recognized a bunch of things, and these are the positive logits, and it's, yeah, weird. Yeah, they do strange things. Yeah. So like it recognized who is our, like the company, but we don't know who they are because it's not a part of this sentence. And yeah, just this one really like took me back. Yeah, because anyway, no, it's Caribes. Yeah, anyway. That's like funny. Where was I? I was here. Kind of thing that relates to Golden Gate Bridge thing. It does really look similar. Determine a poetry head and boost that? Huh? Huh. Yeah, no, that one was really like cool. And that does look very similar. Even visually, you know? It's Gemma because it's from Google. Got it. Okay. Yeah, we can post this somewhere on Discord later. That's really cool.
What is model? All right.
Yeah, it's okay. Sometimes I can't focus or I can't understand, so thank you. It's still really cool. The probes have been trained on, oh my god, so probes have to be trained on one thing? Okay. Oh hey. Oh right.
So what is model interpretability? So this is my definition here. This is the study of understanding the internals of models, for example, their weights and activations, putting those insights in human intelligible terms.
Hello, Oliver. I feel like saying the name Oliver in a British accent because it feels, yeah. It's been a while since I've watched Oliver Twist, but I like it. I don't think I've read it. I should.
Models, for example, their weights and activations, putting those insights in human
sparse autoencoder models that get trained just to try and understand what a head is doing in a specific model. Cool. Okay. I got like 50% of what you said and I'm happy about it. Okay, encoder. Not even the output. We want to know what's happening like early on, right? Because the output we can see.
Intelligible terms and using that insight to both patch current models and develop better ones. If we're not sort of able to do both of these things, patching current models and develop better ones, we're kind of doing interpretability for interpretability's sake. That's nice and fun, but it's not as applicable for the community. So you've probably heard of the term mechanistic interpretability.
No.
In my opinion, a subfield of model interpretability. And this is sort of my definition. It aligns reasonably well to the core mechanistic interpretability people. But it's the study of reverse engineering parametric models, often neural networks, because that's what we use, from their learned weights into more human interpretable algorithmic units. And often they call these things circuits. And these are basically functions that you can describe in a human interpretable way that sit inside models. There's a bunch of notable work, again, for the sake of time, I'm going to just briefly talk about them. So the first one is they look into analyzing small MLPs and transformers to build out the intuition of what circuits exist. And a lot of this work came out of earlier work on LSTMs and doing similar sorts of things with LSTMs. And they find a bunch of things. One thing that they find is this idea of induction heads. And these induction heads, they say, is sort of helps prove why models can do in-context learning. So an induction head is something that it's a specific attention head that kind of allows you to, when given a prefix, allow you to kind of copy the necessary resulting token from the underlying training data that the model's seen before. So in context learning, what you generally provide is some sort of prefix, and then you provide some example, and hopefully, you can classify the thing or something like this. It's saying that there's these attention heads loosely that exist that are able to copy or unearth that information for a specific context. Other things that they've done is on neurons. So this polysemanticity. So what this kind of means is that your neuron is you have a set of neurons in your activation space. So let's say at layer 10 in your model, you have an output. And so your activations is, let's say, 1,000 dimensional here. Each of those 1,000 individual neurons may represent more than one specific feature. And so they talk about this in that context, and this is kind of a theory, but you can think about trying to process input. And when you're processing a vocab of size 50,000 or 250,000, at some point in the model, we're actually compressing it down to the hidden dimension. And so in some cases, that looks like you're trying to compress a much richer feature representation down into a smaller set of neurons. So it is reasonable to believe that a specific neuron will represent multiple of those features. And given the structure of our weight matrices, it is the case that if they are representing more features than number of elements in the actual, or the number of neurons in the activation space, then many of these features are linearly dependent. And so we're not really able to utilize them that well. They talk about this. They don't talk about this in the best way, but it seems kind of clear to me that since you have embedding matrices that are not square, that these neurons have to exist, and they have to incorporate multiple features at once, multiple redundant features at once. So before I move on to the rest of model interpretability, any questions about mechanistic interpretability?
I hope someone asked the question.
Oh. Mentioned that you apply sometimes and then others. Where, like, for instance, the induction has worked for different types of arguments.
So most of their studies are for a very small set of models, and most of these are old GPT models. There have been a few works like in the last couple of months on doing this for the llama-based models. It seems like this is a more general phenomenon for language models. It also is the case that certain attention heads specialize, and we'll talk about them a little bit in the activations part. But yeah, they're not, like, all attention heads aren't created equal, even though they start this way. And it seems to be a general principle across.
Cool. The heads doing multiple things might be why you saw seemingly unrelated words. Other words that activate the same heads in the gemoscope. Cool. That is really cool. Like, I'm not there, but I'm looking from the outside.
One other thing, you might know about this better than I do, but I think there are some preliminary works that say that transformers seem to be particularly good at doing things like induction heads compared to kind of recurrent models. And there was a paper really recently about comparing, like, Mamba and in transformer-based models. Mamba being a kind of more like closer to a recurrent network, which we're also going to talk about with class. But so I think there's some indication that transformers actually kind of are key, or are at least, like, better at kind of in-context learning than other architectures are. So there is some.
I do not expect him to be in the class. That's cool that he's there and he's asking questions.
Interesting implications of that, which is like, well, if transformers are good, what's better than transformer? Yeah, like naturally learning this sort of thing. So
they're good at, they're like really good at copying and like maintaining information, like more so. And yeah, I think it'd be cool to like be able to know how to do this, but be able to extract that kind of information, like what of the transformer is actually helping it do this copying mechanism or like being a better in context learner, then we can develop a better structure, a slightly better structure than a transformer. Hopefully someone comes up with that soon. But cool. Anyhow.
If they are orthogonal conceptually, there shouldn't be much interference by the heads activating for very different categories. Golf equipment and say Java. Okay. I don't know what orthogonal means, to be honest, so I'm gonna Google that. Sorry. So if they're really separate, there shouldn't be any interference, but right angle. So they're at like different points. Cool. Thank you.
Other questions? All right, so let's move into model interpretability. So there are weights and there are activations. I mentioned these are the two things. These are the two things that we're going to look at. So what can you do with the weights of an already trained model? Really, you can just edit them and then kind of see what happens. The activations, similarly, you can look at the activations for different inputs. You can poke them with a stick and see what happens. A lot of my research is poking models with a stick and looking at the activations. It's like predominantly what I've done, so we'll talk about that. And the technical term for this is intervening on them by adding some vector or other sort of manipulation to the latent space. But really what you're doing is like poking with a stick.
That's cute. Poking with a stick. Yeah, that's fun. Like, it's lucky to, I'm sure in the United States you don't get paid to do a PhD. You have to pay for it to poke things with a stick. But still, to just do that. That must be fun. I mean, you don't get paid here as well, but there are places where you get paid to study, which is nice.
So when you look at weights, one class of methods or area is on model editing. Fine-tuning is like the most extreme version of model editing. Usually these things are much more targeted. So in the model editing sort of landscape, your goal or your target is you have a concept or a specific fact that needs to be changed in the model. And your approach here is you update or edit the weights of the model to edit the model's belief of that fact or concept. And ideally, you do this without changing any of the other behavior of the model.
Hey! Oh God, sorry. This is like the Golden Gate Bridge, isn't it? And this is before that. It's way before that. If you see, this is 9 months ago. Changing a model's belief. This is funny, isn't it? Like if you said that a few years ago, you're like, well, there's a runway model.
For example, let's say you're trying to say that Graham is no longer a professor at CMU, but is a professor at Stanford. You don't want every single person at CMU to now be a professor or now be affiliated with Stanford, right? Graham, please don't go to Stanford. So here's one approach, a paper that came out a couple years ago. There's a lot of work down here in the model.
Going back a while. Can you hear the rain?
Model editing world. I'll give you sort of a really brief overview of this. But basically, they have facts that they want to manipulate. So for example, the example that they give in the figure is they want to associate the Space Needle with Paris. The Space Needle is a cool needle in Seattle, has nothing to do with Paris, but Paris also has a tower, so yeah, it's close. So they use causal tracing to isolate the causal effect of the individual hidden states for this fact. So they basically continuously perturb the input, do a bunch of forward passes, and sequentially find the specific hidden states that are associated kind of with this fact. Then they make an edit, and their edit looks like this thing on the right. So they treat this pair, Space Needle and Paris, as this key value pair, where Space Needle is the key. You pass this into into this weight matrix, this original part of the model. You want this now, instead of outputting Seattle, to output Paris. And they have some nice math and a closed form solution to identify this. This is super expensive because they have to, the like, causal tracing part, they have to do a bunch of forward passes. And they make this a little bit better in future work. They also do sort of a more comprehensive edit. So
This is from 2022. The other work could be like built on this.
these are kind of like some of the things you can do. I'm less excited about model editing. There's some work on model editing, sort of. It's hard to control what other things break. And there's some work with when you edit a specific fact, things start being weird and being biased in other ways. And so, yeah.
Just to clarify, do all kinds of factual information of X is in Y, or would they all correspond to this one layer, or is it just with this specific example?
For this specific example, it looks at this specific point. For every example, they'll probably find different regions and a different degree of manipulation. And yeah, that it gets a little unprincipled kind of quickly. It's not.
It was huge. I agree with you. Both because they were able to do it on a huge model like Claude, yeah, and because they went further and showed that once one could do stuff like boost a hit activation and get interesting output, where this stuff is like more basic. Which head do we do a specific fine tune or attention? Oh, to have a blunt effect. Yeah, the effect was like really loud because I remember the Golden Gate part was like one example. There were a bunch more about more malicious examples, right? That was, like you said, it was huge. Yeah. I think, like, I don't know. Did I know about Claude before then? I'm not sure. Sorry, I don't know what that means. Attentive? Wait, sorry. Like to tune down the volume of a tune. Wait, I don't know. Anyway, knob of its influence. That's cool. I'm learning words today. I just need to know how it's attenuate. Yeah, I think that's the word. Yep. Nice. Thank you. Reduce effect value of. Okay. Yeah, you did misspell, but it's fine. There was an extra T in there.
Not like they're able to find, a specific attention head or a specific layer or specific weight matrix that corresponds to like all, relations of a specific type. Any other questions?
This is actually just a question if you know. It seems like more frequent facts might appear in more places in the model. Do you know if that's actually the case?
I have no idea, but I would imagine that it probably could occur in more places, but also a lot of the information is redundant anyway in the model, especially for larger models. So you might have to make targeted interventions in multiple places, but it's possible that one intervention in one place sufficiently destroys like contextualized information in other places if it's close. It depends on how.
I guess there was no example of like model being destroyed as well about the Claude one, right?
How big this intervention is, if it's like hitting it with a hammer rather than some like nice fine grained thing. But that'd be a good experiment to see. Any other questions? All right, so we'll move into the stuff that I'm most familiar with in some of my work. So looking at activations. So this is work I've been doing for a while, this idea of steering vectors. So I mentioned I poke models with stick. Steering vector is that stick. So it's basically a fixed length vector that steers a language model to generate a specific sequence exactly when added to the hidden states of a model at a specific location. and I'll read this again. There's a very like specific form that I wrote this in. So it's a fixed length vector that steers a language model to generate a specific sequence exactly when added to the hidden states of a model at a specific point. So this is different than a soft prompt or different than a model editing sort of approach. In this case, there is a vector that corresponds to a sequence, and that vector doesn't correspond to any other sequence. There could be multiple vectors, and it turns out there are multiple vectors that correspond to that sequence. It'll be a little bit clearer based on how we extract these things. So this is the stick that we're poking the language model with. So how do we extract them? So this is GPT-2. Basically, this Z steer thing on the left, this is the steering vector. This gets initialized randomly with small, like in a reasonable way, uniformly and small. And for any sequence, a specific sequence that we want the model to generate, we optimize this steering vector, Z steer, to generate that sequence, keeping the rest of the model entirely fixed. So think about
Okay, I was about to ask a question, but I'll let him.
it as we're nudging a frozen model to be able to generate a specific sequence at a specific time.
Huh. So we're not updating anything inside, but from the outside. I was like, does it feel like it's like changing a weight? But I guess not, because if it was a weight, it would have consequences, like other things would change with it.
And we have a lot of different options on where to inject the steering vector. We can put it basically anywhere in the model. We can put it at any time step, any number of these things. In practice, providing it just at the first time step and somewhere in the middle of the model, basically not the first layer and not the last layer,
okay,
works pretty well. And so more formally, forget the kind of notation, but right here we initialize this Z steer, and for a few iterations, we do forward passes. First, this starts as random, and then this gets closer and closer and closer to being able to generate the sequence. And eventually we get to a point, and this n is pretty small, it's like 8 or 10 or something like that, for most sequences. We get to a point where we have found this stick that is allowed to poke this model to generate that sequence exactly. Now, when we greedy decode from the model, we pass in just a beginning of sequence token and this Z steer, the steering vector, and it's able to uncover a whole sequence, that whole sequence that we had at the beginning entirely. This is weird and interesting because in a lot of cases, in like the prompting world, in the soft prompt world, usually you need a pretty large width of a prompt to be able to do things with. And this generally in that structure, you're doing a specific task and you're providing kind of a large prompt to do this with, large soft prompt to do this with. This often has a width of 50 and a length of the hidden size or the embedding size of the model. In our cases, all of our steering vectors are width 1, and they're of just the hidden size of the model. So what ends up happening, actually, before I go to results, any questions? This is a weird setup and weird relative to what other people do. So happy to take any questions. Yeah. Similarly, if your prompt was of a specific type, so the prompt here is a continuous vector passed in, it's a single length with hidden size continuous vector. So it's kind of like maybe collapsing your prompt into this, compressing it into this tiny vector. You can think about it that way, yeah.
So
any other questions? Yeah.
So like, for instance, this would be like free, but I'm just thinking like using steering vector would also be pretty good for like things that are typed.
Potentially. This is something that I wanted to work on like a year ago and didn't get the sufficient buy-in, and then had to apply to grad school and all these things. So it went by the wayside, but definitely something to something to pursue. And there's a lot of scope there. But any other questions?
So the output would be what results
All
from
right, so move over
the
to
changes.
results. So we can find steering vectors, and that's interesting. And we can find them pretty easily, and for most sequences, even sequences that the model hasn't seen before. The
Find them? Like the number?
underlying language model hasn't seen before. It also works for, and this is kind of a negative, but it also works for random sequences
Okay.
of very small length, but it's harder to find. So you can imagine if your steering vector is basically a giant bulldozer, it doesn't matter what your model has learned, similar to the probe situation. If you can compress all that information of that sequence into the vector.
For the steering vector, does it feel like driving as if you're in the movie Bird Box? So you can't see anything and you're trying to get somewhere. And then when you find the path, you get this like beep, 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 you got it. From tokens to words on inner lexicon of LLMs. Hey, thanks. Oh, is that 2024? It is October. I can read the title now. Here we go. There we go. They find where the model combines subwords into words and able to make embeddings for those words. I'm gonna quickly read the abstract. Natural language is composed of words, but modern LLMs oh yeah, that's true. We do process subwords as input. A natural question is raised by this discrepancy is whether LLMs encode words internally, and if so, how. We present evidence that LLMs engage in an intrinsic detokenization process where subword sequences are combined into coherent word representations. Our experiments show that the process takes place primarily within early and middle layers of the model. Wow, that's so it can recognize a word, but inside, not outside. They also show that it is robust to non-morphemic splits, typos, and perhaps importantly to out of vocabulary words when feeding the inner representation of such words to a model such as input vectors that can understand them despite never seeing them during training, or findings such as that LLMs maintain a latent vocabulary beyond the tokenizer's scope. Wow. These insights provide a practical, fine-tuning free application for expanding the vocabulary of pre-trained models by enabling the addition of new vocabulary words. We reduce the input length and inference iterations, which reduce both space and model latency, with little to no loss in model accuracy. Ooh. I think it may relate it to what he was saying. It is though. Like it has to do with like messing with what's inside. Except they're limiting the sequence to subwords that represent a word or a word phrase. That is really interesting. I'm too lazy to read full papers, but yeah, thank you for sharing that. You can put it on Discord if that's all right with you. If not, I'll do it.
You don't really need the language model. So there are cases when you're looking at sequences of length like 5, 7, 8, something like this. You can uniformly sample from the vocabulary at random with replacement, generate utter garbage, and find steering vectors for them. Takes a little while, but your model is complex enough that you can basically bulldoze your model to be able to do this, even if that sequence is incredibly low likelihood under the model. But it works better for things that are higher likelihood under the model, predictably. I think the thing that surprised me the most was these steering vectors themselves have interpretable properties. So distances in steering vector space reflect semantic similarity. So if you have two sentences that are close, they're also close in steering vector space. That's kind of nice. It does better than, for example, the representations one would use for probing. So mean pooling BERT hidden states, like we looked at before, those do actually worse than steering vectors. Just a bit surprising. Style transfer is possible with simple vector arithmetic. So it'd be nice to say that I have a sequence, I want to subtract, negativity and add positivity for sentiment or other sorts of styles. We can do this, and we can do this reasonably well in steering vector space. We can also decode from interpolations in the latent space. So you take two steering vectors for two sequences, you look in the middle of them, you linearly interpolate between them, and you decode. If the space is kind of weirdly peaky, then you would have issues, and what you would generate is garbage. And there's no guarantee that the space should be reasonable in between them, but it turns out it is. Here's an example of one of these style transfer cases. So very, very simple, easy sentence. We found the steering vectors for the taste is excellent. And we took a sample of 100 positive sentences and 100 negative sentences, found their steering vectors, took the mean, and thought that, that looks like the positive concept steering vector, or negative concept steering vector. We just did vector arithmetic, just did current steering vector.
I think it would really benefit us if we look at the most recent lecture on interpretation by Grant Neubig. Not today, obviously, because I'm out of time. And I want to finish this before I go. But yeah.
Plus negative minus positive, and we got the taste is unpleasant. And similarly, in the reverse directions. It turns out that the magnitude matters because for every single sequence, there's kind of an n-dimensional ball around that steering vector that we found that also decodes that specific sequence. And so that shows that the space is kind of reasonably well formed. There's of course a lot of weird sort of areas. And so if you go poke around in steering vector space and sort of try to sample from it, eventually you'll find some weird edge cases and some garbage and repeated text and little things like this. Any questions here before I kind of rapid fire through the last few things? Yeah.
I wanted to there's just heuristic magnitude that you don't have.
Yeah, so we went beyond this. There was
It is. The lecture is from 9 months ago, which is not that long. It was from spring. The things that have been learned since it. Yeah, when people say they're interested in computer science or machine learning, I'm like, be ready to not rest if you feel like it. You can rest if you want, but yeah, yeah, it's fun though, isn't it? The sad part is, as an individual, you feel like you'll never get there because companies are going so fast. But it's also interesting to learn from them, what they're doing. Take what their lesson learned, because it's really costly.
In these specific experiments, we looked at the middle of GPT-2. So this was layer 6, layer 7, and at the first time step. We didn't do any magnitude scaling. And so you can imagine if you put a giant vector in there, the rest of the model has never seen something of that magnitude. So it's now in a weird state and it's just going to break. So if you put this to 500 or something like this, it breaks. It just has no idea. It's basically telling the rest of your model, hey, it's a completely untrained model. It looks similar to random performance. You get repeats and things like this. Smaller, you end up staying in this ball for this sequence. Two seemed pretty reasonable.
What's a moat? OpenAI? The ones that think? Unique competitive advantages that a company... Huh? Sorry. It's a normal word? Oh, I don't know that. Okay. Huh. Uh-oh. Is the water around a castle? There we go. Thank you. Whoops. Hi, hello. Okay. Oh, okay. See, I know what a moat is in that sense, but I didn't know what it meant. They are trying to build, or no, it's all right. They are trying to, yeah, like they're doing not that obscure if you've played Clash of Clans, or watch fantasy. Okay, we have no modes. I didn't know about that one. But now I'm looking for it. Right. Yeah. Because sometimes the open part of OpenAI is being questioned more recently, right? That's cool. Okay. I need to go like 2 minutes ago, but I am going to finish this one.
But we didn't spend a lot of time. Just like the day before the paper was due, and we were like, 2 seems reasonable. We went to 3, we went to 5, 10 broke, 5 somewhat broke. 2 seems reasonable. Decent.
It's cute that he's talking about they have 2 examples because 5 broke and it was deadline, so they were like, let's just send it.
Signing, hopefully. Cool. So I'll talk about a similar type of work came out more recently on inference time intervention. So basically, they use some of the ideas that we talked about earlier. They use linear probes to find attention heads that correspond to a desired attribute. They did this for truthful QA. So their hope was to find truthful directions in latent space. And then they shifted the attention head activations during inference along the directions determined by the probes. So what this kind of looks like is you take your attention heads, you probe them, so you stick a classifier on top. This classifier learns to disentangle sort of truthful and untruthful, and now you have a hyperplane, and then you can move orthogonally to this hyperplane in the direction depending on which way you want to shift. So if you want to move towards truthful, you can move in that direction or away. And they do this, and it works pretty well. I think they do this for the GPT model and maybe a llama model, but can't remember the exact details. And it's a similar intervention. They basically add this vector that they find, and they have a little note on scaling. If the magnitude of the thing is too much, things break. So they like hyperparameter search for the sort of magnitude of activation. But it's sort of a very similar approach to what we did, but this focuses on specific attention heads. And they don't do this for all the attention heads. So back to like your question earlier, do attention heads specialize? It seems like they do. And so there are many of them that have like no probing accuracy or limited probing accuracy and actually are like distractors for the truthful direction. Any questions here?
Attention heads specializing. That is interesting.
Cool. So more activation manipulation. So there's some work recently on contrastive steering vectors. So the way we did this like sentiment steering was we had some positive sentences, some negative sentences. They weren't tied together in any reasonable way. We found their steering vectors separately. You could imagine the case, and maybe a more useful case, with 2 prompts that you can design that go 2 different ways. You can sort of find their representations and do the manipulation, the differences here. like individually rather than for a whole concept or a whole attribute. And the value here is your context is preserved. So if you're doing something like, you're doing retrieval-based things now, you have some sort of document and then you have a question. If your question sort of, if you want to ask it in two different ways for two different things, this would be a much better approach if you want to use steering vectors than the stuff I was doing. And it seems to work a little bit better. They didn't compare against our things because it's not like an apples to apples comparison, but it seems to work better and be more general and be more useful. Any questions?
No, because I need to go.
Cool. So what can model interpretability give us? And these are my concluding remarks. So hopefully we get a better understanding of how language models work, their internals, their structure. We get to understand kind of why they do really well. This is still like very, very unclear. And hopefully we find lightweight methods to control and steer models. As models become more and more useful and impact more users, we need better ways to control and steer them. And it's unclear how much industry will devote to these things. So it might be the role of
1 minute left, it's fine.
Do more science in order to figure out how to control and steer these better. And hopefully we can also find potential alternatives or complementary methods to do alignment. RLHF is kind of expensive. And if we could do this with limited data and exploit structure and information that's already in the model, more so than these methods, maybe we can align them better. And these things don't have to be alternatives. They can be complementary to RLHF. Here's some resources. This is an extremely incomplete group, but here are some folks that work on model interpretability. There's many of these. I cited some work from some of these teams, but there's a lot of people working on it. And in the last year, there's been kind of an explosion, especially in the mechanistic interpretability kind of world. Sasha Rush had a recent tweet that asked prospective grad students what is the topic that they're most excited about, and mechanistic interpretability was the thing that seemed to have won out.
Wow.
So I encourage you to kind of dive into this literature and read some of the papers if you're excited about it. And yeah, thanks for your attention. And that's all I have.
Yay. Clap, clap. Sasha is the founder of HuggingFace, right? According to my knowledge. I did not expect to have the energy to stay this long. Yay me, and yay the people who are watching for giving me the energy. I really was not planning to. I mean, I was planning to stream yesterday, but then when I woke up this morning, I was like, really? But then I was like, why not? I like the nice people that talk to me, and I am thankful for that. Yeah. So, oh, sorry. So, thank you for sharing the links with me on Discord. I'm gonna go through them later, especially the video ones. And you're right, it was the Tom Nicholas one that I was talking about, the British YouTuber. I'm curious about the other one you sent. Yeah, thank you for being here. I wish you have a lovely day. Oh God, what happened? Did internet cut off? Hopefully no. Guess not. Okay. Yeah. I am not sure, I don't think I'm gonna stream Study With Me today because it's Friday. Let me just rest a little and actually probably watch Squid Game. Yeah, I'm so excited about it. Wish me luck on that. Yeah. Okay. I'm gonna go have breakfast. That's the thing I've been hurrying to go to. Okay. thank you for being here. I'm gonna see how the goodbye thing works with the microphone. I wish you a lovely day, and if you have the energy, see you next time. If not, ooh, the microphone went down. That's cool. If not, that's all right. You can, yeah. Yeah, thanks for being here. And see you next time, inshallah. Goodbye.